So hello. So you can hear me? Hello, hello, or
Yes, I can hear you.
Yes.
oh, great. Okay, thank you, thank you. Okay. Oh, and great. And there's more and more pictures. Great. I feel like. Why do I feel like? Okay. All right. Great. Um. So we're finally starting to progress, but of course I'm falling more and more behind. One thing some of you might have. Oh, thank you, thank you. Some of you might have noticed this on your own. I hope you did, but I totally did not. I failed in more than one duty over this past weekend, and that is um, I did something that I'm going to do again, but I wanted to warn you in advance. What I did last time, you guys, this section, I gave a long lecture where I was trying to move from the material of planet Earth and of the hypothetical train. I was trying to get from Galileo's principle of relativity um, to the actual kinematics and the actual mathematical looking physics that we really have to do. That was the lecture I gave to you guys. Then in the other section right away afterwards, and some of you may have noticed this and some of you may not, right after that with them, I just dove straight into going over the problems for number line and my like the more direct problem solving material. My intention, what I wanted to do was then I posted both recordings. I did post both recordings, so it is possible that some of you noticed this fact. But I did not alert any of you. What I'm trying to say is that I tried to set it up so that I did one particular lecture in each of your classes, but then I wanted to ask you all to make a point of watching the other lecture as a recording. And that way we could cover that much more material and not lose any ground. I did not ask you to do that. I failed to do that. So, but I want to say it now before I forget that I may do that again today and in a number of future times. In other words, when I post the videos at night or whatever we did in the morning, um, especially if I alert you to this fact, please make a special point of looking out for the lecture for that day that wasn't your section, because it's distinctly possible that I would like everybody to see both so that I can cover both things that way. Now, again, I didn't ask you to do that explicitly for this time. But some of you may have noticed I'm not. So what I'm going to do now, I want to start really going over these problems, but I don't want to waste anybody's time. So I'm going to go through these number line problems. Okay, so this is a long way of saying the very first homework that was assigned. It was assigned a while ago and assigned, or not the very first, but the very first sort of numerical looking homework. The sheet called number line. It's been sitting in your dockets for a while now. I want to make sure we have the right answers and we're doing it correctly. I'm not going to talk. I'm going to sort of fly through this. I'm going to ask everybody if they have major questions to go back and look at the lecture that's online. But right now, I'm going to sort of fly through it, meaning I'm going to say what the answers are. I'm going to show you how I did it. But please, I'm flying to not bore you and to get to the other stuff. But I'm flying through the stuff that I think maybe you don't have questions. But if you have any question about any part, please stop me. Like, don't. I'm not assuming that this is all obvious material. I'm just assuming that I did post a lecture, and so I don't. Anyway, I think you get it. So I'm going over number line, which is the first sheet. My goal is to get through this one quickly so we can get to the second sheet and third and start catching up with ourselves. Um, but these are mostly about taking definitions really seriously. So we've got, so all right, so here's the number line situation. So everybody's with me, yes? I know, good morning, welcome back. Welcome to Crazy Land. So the whole situation of this homework sheet is supposed to be like, welcome to the world as we view it as physicists, not when we're just starting out as students, but when we are starting off our thinking about space and time, when we're laying down terms and everything, we picture one dimension of space and one dimension of time. One dimension of space means 1 degree of freedom. Like you can walk forward or you can walk back, or you can call it left and right, or you can call it north and south, whatever it is. It's one choice that you can make, whether to go this way or that. And so we designate the two options, positive and negative, all relative to a 0 that is up to us. Like the 0 center piece of this number line is whatever we say it is, but then because of all the Galileo stuff, because the laws of physics are going to be true in any reference frame, in any coordinate system. So we place down our coordinate system. We say, here's our 0. Everything to the right of it is positive. Everything to the left is negative. We could have done it a different way because the laws will be the same no matter what. But here's our coordinate system. And now we're going to make measurements based on that coordinate system. Okay. And the situation here that we happen to be looking at is a professor who starts at position. Oh, this is badly drawn, actually. He apparently starts at a position called +4, just trying to highlight the fact that he doesn't have to start at 0. 0 is just wherever it is. So here's, so he starts, here I said I was going to fly through this and I'm already not, but the professor starts at position, or the instructor, the person at the front of the room starts at position +4. He undergoes 3 distinct motions, and they're each distinct or distinguished by a constant rate of motion that characterizes each one that we ultimately figure out. But okay, the diagram is just a rough diagram trying to show that he goes all the way to the -2 position on his first pass, then he comes back to the +4 on the second pass, and then on his very last pass he goes all the way to the end to -5. And each of those passes takes a certain amount of time that we're told, 3 seconds, 2 seconds, and then 3 seconds respectively. All right, this is called one-dimensional motion. This is the setup. I'm going to the next page. All right, now we're just applying definitions here, but so this is where I'm going to hopefully make it fly. I say the total distance that it covers is literally the total amount of ground traversed, the total amount of space that he passes through, ignoring or not making any distinction about directions, just adding up like all of the actual space that he traverses. So it's like the absolute value of each segment is how I think of it. And so I'm getting 21 feet. Here's where I'm saying, like, if you're with me, great, then I'm going to move on. If you're not, please stop me right now. But I say the answer to the first question. And also, if I'm totally misremembering what we did in class, like I think we have not technically done this and people want me to do this, so I am doing it. But please stop me. I think the answer to the very first question on number line is 21 feet. But then the next question is, what's the total displacement? This is literally just, we're defining one word one way, the other word the other way. You might your whole life think that it makes more sense to flip the two definitions. Totally fine. Like it just happens not to be the way we use the words. But the really important thing is, can you hold the two different concepts in your mind and know that they're different? This concept of displacement is literally how much something is displaced. It takes into account the fact that there's direction distinctions. So this is, in a way, you could almost argue our first actual equation or definition. The definition of total displacement for any journey or for any set of motion is the final position that something ends up minus the initial position. I don't remember. Yeah, I think I've given you this notation. Yes, yeah, we talked about this notation last time, I think. So we're using X from now on. X means position in space, like point in space. T stands for moment in time, point in time. Wait, could someone actually say, did I actually stop and define for your class what I mean by something sub-zero, like X naught? Even if you know it from another class, the question is, did I actually define it for this class, what I mean by X naught and stuff? Can someone tell me? Like, have I made any point about when you put 0 to the right of a letter, what you call that and what it means? Have I said this in this class? Hello. Hello. Wait, can you hear me? You can hear me, right?
Okay.
Okay. So wait, could I just, I hate to like come to a crashing thud, but in this, have I defined X naught? Have I discussed what that means? X naught or T naught or anything? Oh, I'm looking at the chat. Yes, I have. Okay, thank you. All right. All right. So I will keep going. Okay. I thought I had, but I wasn't sure. All right. So the total displacement here, literally, this is an equation if you like the final position that the thing ends up minus the initial position is -9 feet, because he does end up to the left of where he started. Had he ended up to the right of where he started, we would say +9 feet. Okay, so that's that one. Yeah, okay, so this is just showing how I did it. The total displacement is adding up all the individual segments, but with taking into account direction. So displacement is the term, distance is the pure magnitude of displacement. Displacement is distance and direction. Okay. Okay, I think so. If I said this in this class, again, I'm just trying to stop me if you want me to slow this down, but this is just a reminder of what I mean by X. This is what we mean by T. Okay, apparently I said this in this class. If I put a subscript 0 to, and again, I can stop this if you want, but, and also again, this is posted, but if I put a 0 to the right of any variable, it means the initial value of that variable. It means the value, excuse me, it means the value of that variable at T equals 0. So the initial value of X could be 0, but doesn't have to be. It could be wherever. It's all relative to wherever you place your 0. However, okay, so the value of any, take any variable at all, maybe for example, V for velocity, put a 0 to the right of it, and we'll call that V naught, and it will mean the value of that variable V at T equals 0. Therefore, just to be clear, if I put T subscript 0, right, if I talk, and again, stop, if I've done all of this with you guys, please stop me. I definitely am not trying to, give you the same class twice. But if I put 0 to the right of T, and remember, triple equal sign means equal by definition. Double equal sign means equal by condition or circumstance. If I put a 0 to the right of a T, then that would mean by definition the value of T when T equals 0. Well, that is necessarily 0. So the value of T is always, the value of T sub 0 is in fact always 0. And by that, we don't mean by T equals 0, we mean the beginning of time, but that does not mean like the Big Bang, and it doesn't mean the Garden of Eden. It means the beginning of time for a given experiment, i.e. the moment you start paying attention, the moment you start the stopwatch. So you think of the world, experiments don't actually begin and end. What begins and ends is the process of collecting data from the world, and the world is just always going on. So we walk in, start a stopwatch somewhere, when we're starting to pay attention, that's what we consider to be T equals 0. And whatever the center of the coordinate system is, according to us, is X equals 0. Okay, so X minus X naught from now on means displacement. That's what this whole page here is saying. Some books call it X2 minus X1 or XF minus XI. It means position now minus position earlier at time, or position now minus position then. It's the difference between where we were and where we are between any two moments in time. So it's how much we were displaced, taking into account direction, right? That's displacement. Okay. So we have two concepts now, distance and displacement. If we try to relate them to time, average speed is just defined to be, let me back up for a second. We're not going to just, we are physicists. All we ever care about is how things move through space and time. All we're ever trying to predict is where something will be at a certain moment in time, or we're just trying to predict how much time it'll take to get to a certain spot. It's all about where, when, and what. So the simplest possible way to relate how far something gets per a certain amount of time is just to divide one number by the other number, divide distance by time. If we do that, if we look at that ratio of how far something gets per a certain amount of time, we call that ratio average speed. Average speed. Average speed in English is defined to be, it's not like we didn't notice it in an experiment, we just defined the average speed of an object, the rate of its fastness, to be how far it gets in a certain interval of time. Similarly, we then define, so we apply it here to this problem in the homework, how in the entire experiment from beginning to the end, what's the average speed? That means take the entire distance that the instructor traversed for the entire experiment, 21 feet, divide by the entire time, and that is the average speed for the entire experiment. Notice average speed is a concept that applies to the interval between 2 points in time and space. Average speed is how far you got between 2 points in space during the interval of time that elapsed between 2 points in time. Average speed is something that applies to a segment between 2 points in time and space. And the answer that you get here is 21 feet per 8 seconds. You literally could leave it like that as a fraction. That is, it is a completely legitimate measurement in physics, and you certainly don't have to convert the feet or anything. All the information of the problem is given in feet, so your answers can be in feet. You could rewrite this fraction as a decimal and say like 2.625 feet per second. That's completely fine. You can even round that and say 2.63. This isn't a test in like lab level precision or significant digits. We're just trying to make sure we understand that average speed is this ratio that is one average. It's one number that represents a whole series of motions. It is not saying that that dude is going at that rate every single moment or at any particular moment. It's saying an average. So the next question, again, I'm just trying to roll on. The next question is, what's the average velocity? Now that's the slightly more precise concept. That's like average speed, but while taking into account direction, right? So this is now something we can write mathematically, and we will, because we will care about this more in physics. This is the straight up ratio between the displacement through space versus time through time. This we can write as an equation and with symbols, and this is how we do it. And notice, I mean, it is just this simple relationship between one and the other, one arena and the other arena. But even if we write it in a perfectly parallel way like that, like emphasizing we're just doing one interval divided by the other interval, t sub 0, we said, is always defined to be 0. So we don't actually ever have to include that letter in the denominator. So from now on, we say average velocity is for some interval is that displacement traversed during that interval per the time elapsed during that interval. From now on, if we put a bar over any quantity, any variable that we're looking at, if we put a bar over it, we mean the average value of that variable. So from now on, and notice average values will always refer to some segment, some interval between 2 points in time and space. We will use exact quantities to refer to exact points in time and space. Okay, so average velocity is from now on displacement per time. So I guess it asks next, yeah, so this is average velocity. The average velocity, question 4, it asks what's the average velocity for the whole journey of this motion. Well, the displacement, so that means the total displacement of the whole thing per the total time. As you find out later in the questions, you can be asked about the average velocity for any one particular segment. It doesn't have to be a whole, but just like you can have an average in your class, like right up until the first exam, and then your average changes after the second exam, and then you have an average for the whole semester. Same thing here, but here we are being asked for the whole thing. So the final position of the whole motion is -5, whereas he starts at +4. So the difference is -5 minus +4, i.e. the instructor is displaced an entire total of -9 feet, but that takes 8 seconds. So the average velocity for the whole thing is -9 divided by 8 feet per second. Of course, you could write that better ways. You could write that -1.125 feet per second or whatever, but it is negative, and it is totally okay for velocity to be negative. When velocity is negative, that does not mean some weird thing like you're going back in time, where it's like Michael J. Fox and a flux capacitor or something. Negative velocity just means going at a certain rate in a particular direction. So the summary of what we have so far, and again, I know I'm sort of boring myself, but the summary of what we have so far is we have we're trying to measure motions in space and time. We have two types of ways of measuring. A strict proper way called a vector measurement, which is a measurement of something, of a size of some quantity and the direction of that quantity. And just the pure magnitude, just the pure size portion of such a quantity is called the scalar, or like the scale of that quantity. So distance is a scalar, and its vector equivalent is displacement. Average speed is a scalar quantity. Its equivalent is average velocity, its vector equivalent. And in this class, indeed, the assumption is that the scalar quantities are the ones that are more close to what's already in our mind when we're just having intuitions about the world. So we'll often refer to them, and when we're thinking in English, we'll refer to things like distance and average speed. But 9 times out of 10, if we're trying to mathematically analyze something, we're going to use the more precise concepts the vector concept quantities of displacement, average velocities, and those are the ones that we mathematically symbolize into equations. So when in doubt, assume that what we're talking about is the vector quantities, and that's what we do for the rest of the problem, I think, for a lot of it. All right, so now it just starts breaking down, and again, I know, please stop me if this is, I'll look at what time it is. Okay. It asks what's the average speed for just the first 5 seconds. Okay, notice I'm just always applying a definition. I mean, more and more as we get to the end of these these exercises are hopefully plug and chug. They become a little thought requiring toward the end. But the more mathematical this looks, the more hopefully you'll see that the way to show work, what I mean by showing work or doing work, especially showing work is really important when you don't know how to get an answer. Knowing what to do when you don't know how to get an answer, you find by forcing yourself to show work when you think you do know how to get an answer. And the biggest, most important thing about how to show work is to start with triple equal signs and move to double equal signs. Like I'm always starting with a definition. If they ask me what's the average speed from blah, 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 I think to myself, what is average speed in general first? Then I apply that to the particular problem. And that becomes easier and easier to see when things are written mathematically. But anyway, the average speed, so average speed in general is total distance over total time. Here, the total time that they're asking for in this question is just the first 5 seconds, the 3 seconds it takes to go out and then the 2 seconds to come back. So the distance I do in those 5 seconds is the 6 out plus the 6 back, like distance. I don't care about direction. So it's 6 plus 6 in 5 seconds. So I'm saying 12 feet per 5. And you could write that as 2.4 feet per second. Totally fine. That is the answer. I don't know where I didn't write it here, but yeah, 2.4 feet per second. That's the answer to that one. And the next question is, what's the average velocity for that same time interval? So notice here, this starts to get into issues. I don't average any velocities. I want the average velocity. I don't take one velocity and average it with another. I just stick to the definition. What's the total displacement per the total time? Well, to go out and then back, the displacement is 0, right? And in fact, I might notice, and I think I write this on the next page, this is a round trip. I'm ending up where I started. My final position is the same as my initial position. So my displacement is necessarily 0. Regardless of whatever my time is below, my displacement is 0. So if you're thinking that this round trip, the average velocity is 0, you're right. And if you're thinking, oh, I guess for any round trip, the total, the average velocity is 0, that is also right. Like, yeah, here. So any closed path you do, any round trip. Now we're in one dimension here. We're looking at space in one dimension. So there isn't really a round trip in the sense of round, but by round trip, we mean anything for any journey for which you end up at your starting point. And for that case, so closed path, in other words, your total displacement is always 0, your average velocity is always 0, which also indicates, for any journey, displacement can be less than or equal to distance, but never greater. And average velocity could be less than or equal to average speed, but never bigger. And for any journey you take, if you actually take a journey, your average velocity and your average velocity and your displacement could both be 0, but your average speed and your distance cannot be. I don't know, for whatever it's worth. All right, so that's that one. Again, stop me. Then it asks, all right, what's the distance? The distance covered from the -2 spot to the 4 spot. These questions may almost seem like they're trick questions. They're not. They're just asking pieces of information that you'll need to put together to get other pieces of information. And that's just the habit it's trying to get you. Whenever you think a question in physics, whenever you think a part of a question might be too easy, don't. It's probably not too easy. It's probably not a trick. It's probably just saying you're going to need this information for some other part. But okay, so from position -2 to get to position 4, that is a total distance of 6, regardless of which direction you go. But then ask, what's the displacement? Well, it is in the rightward positive direction. So the displacement happens also to be +6. It's kind of a dumb question, I know. And again, stop me. Okay. Then ask, what's the average speed for that interval? So it's just trying to highlight, again, don't do anything over fancy. Don't overthink it. Average speed is total distance per time. So the total distance you just got is +6. You put it over the time for that. is 2 seconds. Boom, it's 3 feet per second. It's just trying to emphasize that, or this question is. Then the next question, what's the average velocity? Same thing, it's displacement per time, and the displacement is final position minus heroes. Sorry. Well, yeah, so the average velocity is positive 3 feet per second. Then they ask what's the average speed from t equals 5 to t equals 8. So you have to pause there for a minute, and you have to start a little bit thinking now, but average speed is distance per time. The time is clearly 3 seconds because we're going from 5 to 8. What's the distance? Well, you have to ask yourself where he is at those 2 moments, but at the 5th moment, he's all the way, at the 5th moment, the instructor is at positive 4. And at the 8th moment, he's all the way at negative 5. So the distance here is, 9 feet, and it's in 3 seconds. So the average speed here, again, it's kind of stupid, but the average speed here, again, is going to be 3 feet per second. So, okay, that's my work for there. And I know, I promise you, somewhere I think physics is really interesting, and I think you'll think it's interesting. Every time we're doing it together, I'm thinking like, this is not that interesting. Sorry, but it does get interesting. But these are the answers, and just because it's not interesting does not mean that means it's a joke to everybody. So you are allowed to ask questions. But yes, I think the answer is 3 feet per second for question 9. And then question. And again, I'm going to say tonight, please just check whatever I post in recordings, like check out the other classes first, especially if I'm not giving you any new homework until I give all this back. Please check out the other, because I'm going to try to do something a little bit different in each class. Question 10, what it does question 10? Question 10, question 10 is what's the average velocity for that time interval, those 3 seconds. It's the average velocity for that interval where the instructor goes from positive 4 all the way to negative 5, and he does it in those 3 seconds. So he goes negative 9. He goes negative 9 feet in those 3 seconds. So he goes negative 3 feet per second. Now, why they ask that question is finally because something finally just about almost happens in this whole long problem. They ask that because they do secretly want you to use that in a question or two, and thankfully we're almost done. Like question 11 says, where is the instructor at t equals 7? Now, this is the first time, this is a totally fair question, and many of you may have gotten it right. Maybe some of you got it wrong or didn't get it, and by the way, you still could hand this in. I mean, I think after today, I'm going to say no, because now we will have gone over the whole thing, but you still could hand it in. But we get to question 11 is the first time you might have to think a little bit, because even though all the information you need to do this is here, or maybe it's question 11 and 12, all the information you need to do it is in the problem. There's no new law or formula or anything like that, but you do have to cross apply the information or use it twice or invert it in your mind. That is, here, they're actually technically asking where is the instructor at a certain moment. So what I do in my mind is just flip. Like I'm now getting used to saying, okay, average velocity is change in position per time. From here on in, I do think it is absolutely that, and that's a strict equality sign. That is just how we define average velocity to be, total displacement per time, right? And that's always true because it will never be proven wrong in any experiment ever in physics. Like, let me stress this again, by the way. If this is an equation right here. We don't have many equations yet, it might seem. But believe me, all the equations we ever have are just going to be built from these. And the reason I believe these is partly because they are so simple and so true. When we say average velocity equals displacement over time, we're just saying that the words average velocity stand for the words displacement over time. We didn't find this out in an experiment, so there's no experiment where we can ever find out that it's wrong. So we have this equation. So it does stand to reason that we can just go like this without having to say it every time. We can switch it around, right? So if I know that in that last 5 seconds, if I know that in the last 3 seconds, the average velocity is -3 feet per second. That means every second in that last segment, every second, the instructor is advancing 3 feet in the negative direction. Well, then that means, right, that means if we want to know where the instructor is right in the middle of that segment, right at the 7th second, well, from 5 to 6, he goes 1. And from 6 to 7, he goes another 1. And he ends up at 2. So I'm saying if you believe that average velocity is displacement over time, then you actually have to believe also that displacement equals average velocity times time. Yeah, so this is what I'm saying here. If you zoom in on that last segment from t equals 5 to t equals 8, in that last segment, we've already said that he's going at a rate of -3 feet per second. At the beginning of this segment at t equals 5, he's at the 4 mark. So in 1 second, he goes from 4 to 1. He goes back 3 from 4 to 1. And in the next second, he goes from 1 to -2. So that's why I believe he's at -2 at t equals 7. It's like the first question, all this, it's sort of multi-step, but it is just taking average velocity equals displacement over time and it's inverting it. So that's the answer to that is -2. And then the final question of the whole thing is, what's his average velocity for that intermediary segment, like from t equals 3 to t equals 7? Well, that's displacement over time. The important thing in here is don't make up, like in the last, okay, and again, I do think I've been very boring, and I know, and we've been sitting on this assignment for like a week now, so like, if you never looked at it all, then what I'm talking about is nonsense perhaps, but if you did it like a good person, then all of this might be excruciating, like to listen to, excruciatingly like not interesting. But I will say again, I think you could sort of fly through all the exercises maybe on to question 10, but in 11 and 12, let's just emphasize that even though they take a couple more steps to do question 11 and 12, what you're being asked to do is stick to definitions and just push the definitions that much harder. In other words, when in doubt, don't try to make up something new. Don't try to make up a new definition. When it's asking for average velocity over these weird time intervals where things aren't given, we didn't make up a new idea of how to get average velocity. We're using the same idea and just rewriting it. So from t equals 3 to t equals 7, the total time interval is 4, and the total displacement we want is final position minus initial position. Well, the final position we just solved for in the last question, it's -2. The initial position at t equals 3 is the initial position at t equals 3 is told to us in the problem. It takes him 3 seconds to get from position +4 to position -2. So final minus initial is -2 minus -2. Oh, that's 0. Like in this segment that we're looking at, he happens to go back to where he starts. So the average velocity for the very last question, the average velocity for this intermediary segment where you do have to think, but you can get an answer, is 0. Like that's the answer for the very last question of number line. Let me just look at the time. Hold on a second. Oh, okay. So for good or for bad, I'm going to pause for a second. What I want to do is move on to the next sheet where I think things actually start getting interesting. Like I think the answer is a bit of a surprise to some of the questions. I want to move to the next sheet with this class, and luckily we have time if I'm reading the clock right. So let me just pause for a second. This, as far as I'm concerned, is number line. Are there any, like I feel a little bit like maybe I rushed it, but are there any questions about it? But I also dragged it for 4 days. So any questions about number line at all? Okay, let me put this a different way. Are we good for me to move on to the average speed sheet? Could I get a show of anything? Can I move on to the average speed sheet?
Yes.
And she's like, yes, I really want to gouge my eyes out. This is so boring. Please move on. Okay, I will move on right now to average speed. Okay. And in fact, yeah, I'm moving right to the controversial. I mean, I think the warm-ups are clear. I don't even remember them in my mind, but I think like, you're just plugging in a definition for the warm-ups, and when it asks, how far does light travel in a certain amount of time, you are just multiplying those numbers out, and and it goes very, very far. It is a true number, but I want to get straight to, okay. Okay. Now, this is a really good, this is problem I think is always worth talking about, whether you get it right or get it wrong. It's worth talking about what the right answer is, and it's worth talking about how to get the right answer. Now, strictly speaking, all we have here to go on is a definition too, the definition that average speed equals distance over time. I can write that as the mathematical equation. Like what we're dealing with here is this. Sorry. What's known is that average velocity is defined to be displacement over time, or put in English, the average speed is defined to be total distance over total time, right? And we know, okay, and we know that's known. That's known in general. What's also known about this? So that's known. Known number two is that we know we've got this car that goes up. I don't remember, I think it's miles. Okay, and then the absolute value on the way up is 40 miles an hour, and the absolute value of the velocity, in other words, the average speed on the way down is 60. Like we're not, the one thing is we don't care about direction here. That is meant to make things easier. But what we're told is that it goes up some hill at 40 miles per hour and it goes down some hill at 60 miles an hour, some hill. We don't know the distance of the hill, right? I mean, we can even, and that is a big point for a lot of people. We don't know the distance of the hill, but we do know that it is one distance. We know that whatever this car does on the way up is the same distance as what comes down. So those two things were known. Okay, we don't know the distance of the hill. That is true, but we do know that whatever it is a distance. Okay, now we are asked that the question is, what's the average speed for the whole round trip? Now, to be clear, again, the average velocity, uh, um, the average velocity is zero, no matter what happens, because the car is going to end up where it started. So the average velocity for this whole round trip is zero because it is a round trip. But the average speed is something between 40 and 60, I would imagine. One might think that it's 50 because one might think that you should average 40 and with 60 and come up with the number 50. It is true that the average of the numbers 40 and 60 is the number 50, but we're being asked the average speed here. So the first thing I want to say is, as far as we know in this class at this moment, we know for a fact that average speed means total distance over total time. It might be true that sometimes to get that answer, we should average speeds, but we don't know that. Like the average speed is not defined to be average of speeds. It's defined to be total distance over total time. So that's the one thing so even if other ways turn out to work, they would have to be consistent with that. So I'm going to start by saying, like, if I didn't know anything to what to do at all, if this were in the middle of the exam, if I'm looking for the average speed, right? I'm looking for the average speed for the whole round trip, the first thing I should really do is start with a definition and say, well, I don't know what the average speed for the whole round trip is, but I know by definition, I do know that by definition, whatever it is will have to equal the total distance, the total, like the round trip, the total distance over the total time. Like that's the only thing that's really the only way I could start. But now I look at this. Now this is what happens to a lot of people. Say this were an exam or whatever. I look at, because I am telling you the answer is not 50, but I also totally understand that there's many good reasons to think the answer is 50. And what you really need to know is how you would know that the answer is not 50, or how to find out what the answer is if this is up to you for the first time. So I look at this and I'm like in an exam and I go, okay, average speed equals distance over time. It's like, these are supposed to be T's, total distance over total time. And there's no reason that should lead me astray, because it's a triple equal sign, so it's always true, right? So why wouldn't it work, or what would be the problem? Well, I write it down on an exam, and the problem is I'm about to go fill it in now. My next step should be to go to a double equal sign, fill this in, put this numbers in. And if I'm a reasonable person, as all of you are, I would say to myself, oh, like, I totally do not know the total distance. The total hill distance was not given to me, right? And that is true. In fact, that's why it's an interesting problem. That is the hook of the problem. But here's why I like the problem. I would go to write down total distance over total time. Then if I'm a student or seeing this for the first time, I might say, uh-oh, I don't have that total distance. That's bad. I got to do something now. Now, what a lot of students will do, or a lot of people will do, is unconsciously, they won't write this down and realize it. They'll just, in their mind, they'll think distance over time, which is the right thing to think. Then they'll think, I don't have that total distance. So then they'll say, oh, scrap it. That must not be the right way to do this. Let me do something else, like average the speeds, because I have two speeds. So let me average them. In other words, people will bail out of this procedure because they think they don't have enough information for it. That's okay, except just because you want to bail out of this procedure, you can't just suddenly make up a new one to fit the circumstances. That's going against the whole thing of the laws of physics are the same in all velocities. But more as an exam taking thing, if I get to this point and then I'm like, oh crap, I don't know the distance. What really should be the next thing that goes through my mind is, I think that's the point of the problem. Like that is the issue of the problem. That's what I have to think about now. What should I do? Well, I have a couple of options, but okay, so first of all, so I'm saying average speed. All I know is that it equals total distance over total time. I don't know anything about averaging speeds yet. I know it equals total distance over total time, but I know that nobody told me the distance. So I could think, oh, that's a flaw in the problem. The whole thing is impossible. And like I could protest and walk out. It is possible that there's a mistake in a problem, but generally one wants to assume that it's not the problem's mistake. So the second thing I could do is get all frustrated at myself and say, I don't know how to do this. This is ridiculous, and give up. We don't want to do that either. What I could say is, wait a second. If this is a legit problem, and this is a very important, okay, assuming a very important insight in solving a physics problem, if you don't actually see the solution right from the start, which more and more is the way it really is. If you're solving a physics problem and you don't at first see how to do it, which means at first you don't see how to begin it, which is what happens to students all the time. They say, I can follow this when you do it in class, but like I sit down and I don't know how to begin these problems. Totally fair to say that to a point, but actually that is the point of physics, is to learn how to start a problem that you don't know how to start. And the first way to start a problem that you don't know how to start is assume that the problem is solvable. Assume that the problem is solvable, or that otherwise we wouldn't be looking at it. Assume that it has a solution. And that means, in this case, if you think about it, that's actually a major insight. If the problem is solvable, that means the answer, if this problem is solvable, that means there's a solution, there's an answer. And if that's true, that means, in this case, the answer does not depend on the hill size. This is very important. I want to say this very clearly. Again, I know all of what I'm talking about right now could be too boring, either because it's too easy for some people or too fastly like hard because they haven't thought about it all. But this specific thing I'm saying now, I want everybody to hear. If this problem where you were not given the size of the hill, the issue of the problem is that you were not given the size of the hill. Like, that's not a coincidence. That's not something that makes it annoying or unfair or that's distracting you. Like, that's the purpose of the problem, right? That you're not given the size of the hill and yet you're expected to do something. Well, if it's really true that there could possibly be an answer here without the size of the hill given, that must mean that the answer doesn't depend on the size of the hill. And that's an important insight. It must mean that it is doable without the size of the hill, or put more specifically, that whatever the size of the hill is would still get the same answer, right? If this is a legitimate problem, if it's not artificial and artificially broken, then whatever the size of the hill is will yield the same answer, which means, and this is really important, that if nothing else, what you can totally do is guess. You can make up, and physicists do this all the time. You'll see how much we do this when we solve differential equations in Physics 204. If you realize that what you need is the size of the hill, or you think you need the size of the hill, but that's what you don't have, then that's actually the thing to focus on, not run away from. One thing we can do, in other words, possibility one, by possibility I mean for problem solving, possibility one, try a distance and see what happens. Remember too, this is science class, not math class as such. We are scientists, which means we are experimentalists in the lab and in our head. Like, and I really do want to say this again. There's a way to do this problem without any guesswork at all. Fear not. I mean, if you hate guesswork and you think it's not scientific, I can sympathize, except that I do respectfully disagree. Like, what we have to do in science is develop a feel for how things work and be willing to try things and then know how to test them. So one thing you totally can do here is you can make up a size of the hill, make up a size, and either believe that whatever answer you get must be the right answer because of the thing I said a second ago, or maybe you don't believe that, and that's fine, but then just try an answer, and then try a size of the hill, see what answer it leads to, and then try doubling the size of the hill or something and see what answer that leads to. Like, in other words, try a couple and see what happens to your answer if you think maybe it's going to vary. But you can see a lot by trying things if you're already given reason to believe that you have that freedom. So I am going to try one. Now, again, there's a way to do this without trying if you don't like, but I'm going to try one, and I'm going to follow this Galileo idea. Like, if I really believe that this answer should work out, that this problem should work out, no matter what coordinate system I pick or no matter what size hill I pick, then if it really is true that I can pick any one I want, then what I should do is take advantage of that and try a distance that will make my life convenient. In other words, I'm going to, if it is up, this is always a physics thing, if it's up to me, I should choose make the problem as convenient to solve as possible. In other words, and again, I'm discussing it this way precisely because I know to some of you this doesn't seem like maybe science, but I think it truly more is than anything else. So I'm going to say, just taking the time. I'm going to assume, this goes to 1205. I'm going to assume that that hill is 240 miles high. Now that's preposterous, or I mean preposterously high. But if indeed the hill size doesn't matter, then I should choose a number that is easy to work with. And I think 240, frankly, 120 would also be nice. I'm picking a number that I think is going to be easy to work with because it's divisible by both 60 and 40. I mean, I could have said 120 as well. I could say whatever I want. I could also say, by the way, one. I could say the hill is 1 mile high, but I don't think that's going to be so easy to work with. So I'm going to try this, and again, bear with me. There's other ways to do this too, but I'm going to try 240, and I'm doing this because the only definition, the only equation I have, like again, people always say, I get the equations, but I don't know which one to use when. Right now, we literally have one equation at our disposal. It's all we could possibly use is average speed is distance divided by time, or v bar equals x over t. That's all we got to use. So we've got to push it as hard as it can go. I'm saying now, okay, average speed for the whole round trip, average speed is total distance, or total distance over total time. Now I just made up the idea that the hill is 240 feet high. So then, well, in other words, I'm saying, right, notice I'm not saying that average speed for the whole round trip is the speed up plus the speed down, or the speed up average with the speed down. I'm saying it's total distance over total time. So that means up plus down distance divided by up plus down time, right? Now the distance according to us here, is 240 up plus another 240 down, right? That's miles if we're talking miles per hour here. And the time, I don't know offhand, but I know that time, if speed is distance over time, right? Right. So just to be clear, I'll rewrite this on the next board. If average speed is distance over time, then distance equals average speed times time, and then time equals distance over average speed. I can do with this information anything I want. So in other words, I'm going to rewrite this more neatly, but I'm saying, in general, time equals distance over, and it all becomes easier once we're actually writing the equations, not English, of course. But so I'm saying, so here time up must be 240 miles, right? Divided by the average speed up, which they told us was 40 miles per hour, right? And I'm just, right? Time down must be 240, that made up distance, over 60 miles per hour. So just putting this all together, remember, now I know I made up the 240. I know I made up that 240. And so you might be thinking, well, that's totally not legitimate if you made that up. But look, if we make up 240, we're saying the total average speed, is 240 over 240 over 40 plus 240 over 60, right? If you accept the 240, which I made up, then we have 240 over 240 over 40. So I can go like this. Probably. right? Or sorry, actually, let me do this a better way. I could do that, but a more clear way is. I don't know if you can see. Sorry, I'm being weird. Well, sorry, I'm being really weird. Okay, I see what happened. Oh, yes, I see what happened. I'm sorry. I see what happened. That's what happened. Right. Okay. What now? This is a long. I'm trying to prove something here, so I can't imagine. I would imagine very few people did it this way. I want to show a couple other ways because I'm trying to show something about something, not the actual, just the answer. But I am saying that if you just make up a distance for the hill, which sounds outrageous, but if you just say to yourself, well, apparently the distance of the hill doesn't matter, or if you even just say to yourself, I'm frustrated, I don't have distance for the hill, and I know what I would do if I did have it, but I don't have it, so I don't know what to do. So even if you just make up a distance of the hill so that you can see what you would do with that, and by the way, that alone is a very good idea on an exam, even if you just make up a distance so that you can show what you would do if you had it, then you're getting all of the points, right? Then the only possible points you're missing is that you don't know the distance of the hill. And it's very, very likely that you'll figure out something about it even by trying this out. But anyway, what I'm saying is, so let's say we decide to try making up a distance for the hill. The first important thing is we make up a distance that actually makes our life easy, which I almost failed to illustrate here, but I would make up a distance that's easy to work with. So say I say that the hill, if I'm saying the hill is 120 miles up, and that's my mistake. I'm saying that the hill is 120 up. So so it's 120 up and 120 back. That makes a total distance of 240, right? Again, just making that up. Then if I put the total distance on top, 240, the total and the total time on the bottom, meaning time up plus time down. Well, the time up has to be distance up divided by speed up, and time down has to be distance down, same distance, divided by speed down. So if I just carefully put in these numbers, which I only made up one. I made up the size of the hill. But once I make that up, then it consistently follows that I have 240 on the top of this fraction. I have 5 on the bottom. I get 240 over 5. I get this answer, 48, okay? And that is the answer, okay? But and my point is, like, if you did this problem any other way, if you didn't make up a distance hill for the hill of 120, if you did it any other correct way, you also got 48. So first of all, I am just saying, just by making up this crazy distance, 120, I'm going to get the right answer. But of course, you can say, well, that's ridiculous. Like, first of all, why would I know to do that? But second of all, like, you have to believe that to believe it. Like, you just made up a distance. And that happened to work out, but you know why? But look, in the distance if you look at this page, what I have, I'm putting the distance, if I'm calling the hill distance 120, then what I'm logically necessarily doing by definition is putting twice that distance up on the top, 2 times 120, and then I'm putting the distance in that fraction, in those fractions in the bottom. So if you think about it, of course, at some point, I am just watching those 120s cancel out. Like, the distance I put in, if you think about it, is going into the numerator of this fraction and the denominator, no matter what the distance is. So it is canceling out, no matter what it is. And in fact, the math is proving, even as I just guessed that number, the math is showing me that that number doesn't matter. You could have guessed 60 or 240 or whatever, and it's going to be in all those numerators. So it's going to cancel out no matter what. In fact, to make this much more convincing, and again, I know that those of you who want to think like pure scientists or something might find it ridiculous that I just guessed a hill. But let's be even more scientific about it. Let's say, let the hill distance equal X. Like, that would be scientific if I just call it X and admit that I don't know it, right? Well, then what I'm really saying is average speed really has to equal 2X, whatever that hill distance is, over X over 40, right? Because that's the time up is distance divided by speed, and we know the speed up is 40, plus X over 60. Whatever X is going to cancel out. Oops, sorry. So if you do this, as long as you know, even if you don't know that the hill speed distance doesn't matter, as long as you know that the definition of average speed is distance over time, then you want to directly confront the unknownness of the hill distance. You don't want to try to work around it. So I'm saying the most technical thing you could do is say 2X over X over 40 plus X over 60, and the X's cancel out, and so you'll get 2 over 1 over, and this is what I was confusingly trying to do before. You'll get this, right? And the way to do, I'm just going to write it again over here. So the average speed equals 2 over 1 over 40. This is really the right way to do it, if you like. And how do you add fractions? You get a common multiple. The lowest common denominator. So I would say something like this, and this is the thing I was trying to do before, like 4 over 240 plus, 6 over 240 plus 4 over 240, right? And so then I have 480 over 10 equals 48. Like, no matter what you pick, you're going to get 48. Last thing, though, all of this makes sense, especially if you got the hint or you heard in advance, this is a tricky question, or be careful, the answer is not 50. Then you might think to do any number of these things that I'm saying, like any number of these proofs that the answer is 48, not 50. But you might still be saying, but I still don't see why the answer isn't 50. Like that's all fine, but why is the answer 50 wrong? And here's why. If you take the 40 and the 60 and average them together to get 50, you're not doing something crazy. And again, and this is now the real lesson of the lesson. Like the answer to this question is 48. The answer is not 50. The reason is, yes, average speed is an average, and it should mean something like what averages mean. Like we are calling average speed average for a reason. And what that reason is an average is the one number that best represents the whole, right? Like the average value of something is the one number that would be best to pick if you want to treat a bunch of changing values as a constant. If values are changing, but you want to just pick one number that represents the whole, the lie that is the least false, then the average value is that value. Now, what I mean is this. Oh, sorry. All right, imagine, I mean, these are terrible. I hate to imagine this, but imagine you take a bunch of tests and you always get either a 40 or a 60 on tests, but you get scores like this. If you look at these test scores where you got some 40s and some 60s, your average here, as I think you know, would not actually be a 50, right? Because even though the two types of numbers that you got were 40 to 60, you got 40 more frequently than you got 60, right? The actual average here, the average wouldn't be 40. It's not equal to 40 plus 60 divided by 2. It's not, I mean, you know this. It's not equal to 40 plus 60 divided by 2. It is equal to 40 plus 60 plus 60 plus 60 all divided by 5. Or in other words, it's equal to 40 times 2 plus 60 times 5. That's what's really happening with the car here, is that average speed is how much distance you cover per a certain amount of time. Or let's even say average speed and average velocity. The independent variable here is time. When we're talking about average velocity, we're talking about how far you covered, how far you got in a certain amount of time. So this car that went up at an average speed of 40, then went down at an average speed of 60. If the distance was the same up and down, then the amount of time that this car spent going 60 was a lot less time than it spent going 40. It spent more time going 40 because it was traveling the same distance at a slower rate, right? And in fact, how much less time did it go? Well, that's what the math showed. Is if you think about it, 40 is like 3/2 as fast as 60. So this car spent 3/2 less time. In other words, 2/3 as much time. It spent 2/3 as much time going the 60 rate as it did the 40 rate. We really want to do a weighted average. Right? If you really think about it, I know I'm spending a lot of time saying this, but I want to emphasize our definition of average speed is total distance over total time. Our definition is not average of speeds, but it's not because we're violating the words or trying to change your idea of averages. If you really want to think about how fast on average this car was going, this car was spending a lot more time going 40 miles an hour than it was going 60 miles an hour. How much more time? Well, like time and a half. Like it was, if you divide its journey into 5 chunks of time, 3 of those time chunks it spent doing 40 miles an hour, and 2 of those 5 time chunks it spent doing 60 miles an hour. That's really what's happening here if you want to average it out like that. So of course, since it spent more time going 40, its average speed was closer to 40, like was slower than 50. And farther away from 60. If you really think about it, the minute you hear the figures in this problem, it actually does make sense that the answer is going to be slower than 50. And what it is exactly 48, because it really is like dividing the whole journey into 5 time chunks and saying that 3 of those time chunks were spent on the 40 number. And that's why we got like 240 divided by 5 in the way that I did it, making up distances. It actually does make sense. All right, so wait, what time is that's a lot of 12. Oh, all right. So the answer is 48 by exactly the same reasoning. The answer to the Little Red Riding Hood problem is she can't do it. The Little Red Riding Hood problem, if the whole, I'm just going to say this because it's 12:05, we're about to wrap and the other class is about to come in. So please watch tonight, please, if you have no more homework to do, because I'm not giving you more because I still want to go over this and give you back stuff, please just whatever video I post tonight, watch the other classes video, please, before Wednesday. But let me just say, yeah, with the Little Red Riding Hood, it's 80 whatever kilometers out to grandma's house. She travels out there at an average speed of 40 kilometers per day, right? So if it's 80 kilometers out, but she's going at 40 kilometers per day, on average, that means it takes her 2 days to get out there. But now the whole trip is going to be 80 kilometers out plus 80 kilometers back. The whole trip is 160 kilometers. She wants to do an average rate of 80 kilometers per day for that whole round trip. If she wants an average rate to be 80 for a 160 kilometer trip, that means she needs the whole trip to take 2 days. But she already used up the 2 days on her way out. So it can't be done. She would have to go infinitely fast. I'll say more of that on Wednesday. Oh, sorry. Yes, I'm sorry. Yes.
I'm confused about for the last problem where you got the 2 before the 60 miles per hour and the 3 before the 40 miles per hour.
Oh, totally fair. Totally fair. You mean like right here, right where I wrote it, right here on the board right now? That thing. Okay, because okay. Okay. Because if you think about it, 40 miles per hour is 2/3 as fast as 60 miles an hour, right? Imagine, let me back up for a second. If she went 60 miles an hour on the way up and 60 miles an hour on the way down, that would be the same speed up and the same speed down. If they were both the same, and I'm assuming no matter what, up is the same distance as down is. So if you do the same distance twice at the same speeds, it would take you the same times, right? But she went up at a speed that was like 2/3 as fast as the speed that she went down, right? She went 3/2 faster on the way down than she went on the way up. So I'm saying it will take her 3/2 as much time to go up as down. Like if you made the numbers simpler, it's a little bit easier to see. Like if she went up at 30 miles an hour and came down at 60 miles per hour, if she went up half as fast as she went down, then I would say she would come down in half as much time as she went up. Do you see what I'm? But because she went up at 2/3 the speed as she went down, I'm saying it would take her 2/3 the amount of time to, I mean, so really what I'm saying is this. Hold on a second. I'm saying if average speed is distance over time, then time must be distance over speed. So if the distances are the same here, up and down, the distance, like the distance we'll call x, then the distance going up is x over 40. I'm sorry, right? The time up must be that distance. Sorry, over. The time up must be the distance up plus divided by speed up. Well, the distance, whatever it is, let's call x. The speed up is 40, right? The time down is going to be x over 60. Does this make sense so far or no?
Yeah.
Okay, so so the time down is a fraction with a bigger denominator. If like we reduce like they both have the same distance in the numerator of the fraction. The time up is x over 40. The time down is x over 60. If they were both, if they both have the same numerator, if they both have the same denominator, then they would both be the same times. But one denominator is bigger than the other. The time down is going to be the same distance, but at a higher rate. So, well, I guess. So for the whole round trip, the total distance is 2x. The total time, like 2x because x up and then x down, and the total time we just said on the other page is x over 40 up plus x over 60 down. Does this make sense so far or no?
Yeah.
I mean, what I'm really, well, all right, I'll do one more. So then I'm saying you can, so you literally have 2 times x over 1 over 40 plus 1 over 60 x. Like I can factor out an x from the bottom, I can factor out an x from the top. So I really do have 2 over 1 over 40 plus 1 over 60. I know this is trying to make, this makes it look more and more complicated as I go, I realize, but I mean, what,
So I have a question. So for example, if it would take 60 to go up and then 30 to come down, would you have a 1 in front of the 60 and a 2 in front of the 30?
Right.
Okay.
Yeah, you got it. Yeah, exactly. That's exactly the point.
Okay, thank you.
So that, yeah, okay, good. That's a great question. Yeah, that's great. Okay, cool. Is everybody else cool? I'm glad. I don't think my answer is very good, but don't let her question was very good, and the fact that she hung in there and then like asked that specific thing is exactly what we should do. So anybody else? I mean, I do have to teach the other class now who are waiting, but any other thing like that? Is that? And again, it'll get more and more like this. I'm sorry people have to wait the whole class to get to something like that. But all right, I'm going to end this and let everybody, oh, thank you very much. Thank you. I appreciate it. All right, I'll look in the chat before. Let me see the chat. Oh. Oh, sorry. Okay. Yes, thank you. And that I think. Well, yeah, I guess that answered it. Okay. Thank you guys very much. I'm going to end this meeting, and I'm going to. Well, no, I'm not even going to end. I'm going to let the other people in. So again, all the other classes about to come in, and they may already have. No, I guess they did. Yes, they're all right. So whoever is here, I'm about to do physics 203, but the other section, and I'm just going to start. Okay. Thank you. I'm just going to pause for 1 second. As a clear. Hello, hello, hello. Okay. Oh, hello, hello. Okay. Hello. Oh, so sorry. More people coming. Sorry. Okay. Hello, hello. Thank you for your patience. And at what time? Okay. Yes, it's 12:15. I don't think we're just about to start. I'm gonna try. I'm. There's gonna be another day of me trying to make tracks and catch up with you guys and get the course more moving forward and looking more mathematical and all that. So you are ahead of me. I still owe you a bunch of stuff. I am aware of that. And um, we're just going to keep going through this homework until we catch up with ourselves, which means you're not responsible for anything new until we get to it in class. And I will still take stuff and still give stuff back. People are still coming in. Okay. We're going to still do this thing where when I post the videos at night, please, let's just have it be a general thing that I think this is more incumbent on the other class, but just in general, if I post 2 videos in a night from physics 203, because there are 2 sections, if you're going to make a point of checking them out, please like maybe always check out the other one first, like from the other section, because to the extent that I do 2 different things, that will be more efficient. But today it'll be very similar. What I want to do is just keep going over these problems. I want to keep going over these problems. We went through the number line sheet last time. We're going to go to the average speed sheet this time. Again, trying to get it to be looking more and more mathematical and more worth our while. There are a couple of warm-ups on the, sorry. Yeah, sorry. I think I am giving a bit. Oh, wait. Oh. Yes, if there were only 2 videos available, then that is not right. That is true. Yeah, there seems to be, well, I can tell you, I got to do something about this link. All the YouTube videos, there's different playlists and stuff, but it's true. There's one channel, and it is true that the actual name of the channel is Professor Yaverbaum, because that got taken from this Zoom address or whatever. So the thing to type into YouTube is Professor Yaverbaum, like that. That is the channel. But a couple ways, I'll try to get the link again, but this will work. or should work, even if this gets you to a particular playlist that is not the playlist you like, then you can still link out of that back into the channel itself or this. But it is true. I'm more and more, I think that this is probably our more useful resource. These should be one of these, all of these should eventually get, sorry, to the same. But if someone has a better, faster way, please do write it in. Oh, it does. Okay, great. Great. Okay, thank you. Good, fine, good. No, and I'm glad you're asking because we do need them. Yeah. So more and more on the things that I post will be sort of different for the two sections. So you'll want to see the other sections. Today, it's not the big, what I want to jump into today in your class, I love that picture. That is hilarious. What I want to jump to now is the same problem that I did solve in the other section this morning. And your explanation will probably be slightly more clean. So you don't have to worry about it so much this time. I'm going to go straight to the second sheet, to the average speed sheet. So the homework sheet that I'm going over here is called average speed. There are a couple of warm-ups at the beginning of the sheet that I'm totally, unless someone wants to remind me really fast, they're warm-ups, they're like plugins, they're not supposed to be tricks. So I'm actually skipping them for the moment. Like, one is how much distance does light travel in like 1,000 seconds? And you literally just multiply it out. But the problem I want to get to, where it's worth thinking about and worth talking about, whether you get the right answer or not, is worth thinking about. The problem we're going to discuss right now, and I know I can see people are still coming in and stuff. The problem we're going to go over here is the problem called hill figure on the average speed sheet. So, and again, yes, there's going to be 2 videos posted about this, but the problem says, given. And so please, I'm sort of hoping at this point that everybody has thought through this problem, maybe more than once. I'm thinking that everybody has thought through this problem. Maybe you got the right answer the first time, maybe you got the wrong answer, then you redid it. Maybe you can't get the right answer, but you should. I hope you know what problem I'm talking about. And the given is that we've got this hill and we've got this car that goes up the hill. It's like Papa Smurf or something like that. Excuse me, more people waiting. Okay, what's known is that this car goes up a hill, uphill at an average speed of 40, and stop me if I'm wrong, but I believe 40 miles per hour, right? We've got a car that goes up a hill at an average speed of 40 miles an hour, which means that if the hill is 40 miles long, it takes it an hour to do that, right? And I don't know what the details are at every moment, but I know that on average, it takes 40 miles. It travels at a speed of 40 miles per hour on the way up. Okay, that's a given. Then what's also given is that on the way back down, this car, on the way back down, the average speed is 60 miles per hour. That is also a given in the problem, right? And we're asked, what is its average? And it's assumed that it turns around at the top like super, super fast. Like the amount of time it takes to turn around is not gonna, is so small that it doesn't matter to the problem. And by the way, that is very realistic. Like it's not realistic for a car to literally turn around instantaneously. It is not realistic for a car literally to take no time to turn around. But it's super realistic and super easy to come up with this situation where a car takes so much time to go up and so much time to come down that the amount of time it takes to turn around is negligible compared to those other two quantities. Like it's very easy to construct a situation where the amount of time to turn around wouldn't even register on the measuring equipment that you would use to measure the other two times. And that's all in science that negligible means, right? If it's too small even to register on the measuring equipment, then it's too small for us to say anything about. So anyway, so we imagine that this car is doing that. It's going up at 40 miles an hour, turns around super quickly, comes down the same hill at 60 miles an hour, and we're asked, okay, what's its average speed for the whole round trip? We are asked average speed, not average velocity. So the fact that it's going up and then down is only relevant, it only matters to us in that it reinforces that it's one and only one hill on which all this takes place, right? So in other words, what's given is what was just drawn. Like this is what's given. What else is given? Tacitly given, you could say implicitly given. What's also given is one, average speed is defined to be total distance covered in some total amount of time, right? That is a given because it is a definition, because it is always true and it's clearly relevant to this problem. So it's given that average speed is defined to be total distance divided by total time. It's also given that the distance, in this case, the distance up this hill, the distance up, which we do not know, and which ultimately becomes the hook of this problem, right? No one did tell us the distance up the hill, but we do know that it's a hill, so that the distance up, as unknown as it is, here better be the same as the distance. It might be unknown, but it better be known that it's the same as the unknown distance down, right? By definition. Okay, so all we know about this problem is the definition of average speed is total distance divided by total time. We know here that we've got an average speed up some unknown distance, and we know an average speed back down that same unknown distance. And we are asking, the question is, sorry, the question. Right, so we know two average speeds, the average speed up and the average speed down. We want the average speed for the whole round trip. Okay, now again, what we know is that average speed is defined to be total distance over total time. Of course, okay, so we're gonna get the answer. Now, I might have mentioned before that there is an answer to this problem, and the answer is not 50. There's totally a reason that I understand that a lot of people would think it's 50. I want to address that in a million different ways, but the answer, in fact, is not 50. And I think you can find out that the answer is not 50 by doing the problem correctly. Like, even if I didn't tell you that, it is discoverable that the answer is not 50. In fact, the answer is 48, just again to make it clear. But like, I'm going to do this a couple of different ways and show you. How do I do this problem? Like, why do I say it's 48? And how do I know it's not 50? Okay, well, I'm going to solve this problem the way I am trying to recommend to people, the way I would in an exam, even if I were under time pressure, even if I were panicking, or maybe especially if I were panicking. The first thing you always do is write down something that's true, and then you try to make it relevant. In other words, always start with triple equal signs if you can, and then turn them into double equal signs. Like in other words, you start with definitions because they're always true, and then you apply to the particular details of the problem, details that are only true in the problem. So I start, right? I mean, as stupid as it sounds, I start, if I'm being asked, what's the round trip? Sorry, I forgot to mention, what I'm being asked is what's the average speed for the whole round trip? I only know the average speed up and the average speed down. So how do I get that? The first thing, if I'm asked average speed, I first write down, well, I don't know what the average speed is here. That's what they're asking me. But I certainly know that in general, like I know this is a duh, but I write down in general, average speed is total distance over total time. Eventually, of course, like this is one of the last times we're going to write these things down in English. Like generally this would be an equation, v bar equals x minus x naught over t. But there's a reason I want to postpone that for just like one more example. So I write down average speed equals distance over time. That's what I should write down first. By the way, I should write that down if I think I do know how to solve this problem. Like I think that would be the first step if I knew, but especially if I don't know, if the minute physics problems get hard enough for you to look at one and not exactly know how to begin, which is most people's experience a lot of the time in physics. If I don't know how to begin, the thing to begin with is a definition like this, right? Now, what's going to happen to a lot of people that now would want to start filling this out or something. I'd want to say, okay, in this case, the average speed, like in this case, in this round trip, well, in this case would equal, distance up the total distance, it means the distance up plus the distance down. Okay. So distance up plus distance down all over time up plus time down. Now notice, this is two steps I've just written down. These are not numbers. These are not an answer yet. I don't know what the answer is. I don't even know how to get it exactly. Like maybe I know that this is a tricky question, maybe I don't. But I do know that these two things that I just wrote down are definitely true about this problem, no matter what, right? And if this were an exam, I would get points for having written these two things down, even though I still don't even have a number yet, right? The average speed for this whole thing has to be distance up plus down, because that's total distance, over time up plus time down. It has to be. This has to be true and credit worthy on an exam, no matter what, even if a lot of us might not have written this down. Now, here's what happens. I go to start filling this in. If I'm like many of us, if I'm a good person who's doing his homework, her homework, who has been doing homework her whole life, right? I look at this and I'm like, okay, I'm going to start filling in now. Distance up. Oh, I don't know it. The problem didn't give it to me. Oh, Yaverbaum, that cursed knave. Like, what's his problem? And I might be angry now. Wait, I need to fill in distance. This is a straightforward enough problem. This like doesn't seem that complicated. But I'm not given distance up. I'm not given distance down. So I don't know what to put in for there. And I certainly don't know time up or time down, even if I know that time up and time down probably depend on distance up and down. I will be even more frustrated now. Like, I don't know any of this because I don't know the distance. This is where what a lot of people, right? And I don't, it's true. Like, I don't, off the top of my head, I don't know this and I don't know this. Okay? This is a point where if I've written this much down so far, I've already gotten points. And even if I now notice that I don't know the distance and I now panic, I'm still in better shape than a lot of people. A lot of people wouldn't have written this step down. So they don't realize by not writing it down that now the brain looking at this may well go, oh, I don't have the distances. So I can't do it this way. This is what a lot of people think. Oh, I can't do it this way. Oh, crap. Even if they wrote it down, they'll get frustrated. Like they'll put a big X through it or erase it or start some other method. Or worse, if they didn't write it down at all, they don't even realize that they're starting a different method. What a lot of people will do now is make something up like, oh, average speed must be the average of the speeds. I'll average the speeds. I'll average 40 and 60 and get 50. But no one ever said we're ever allowed to do that. And no one ever would do that. Like no one did that in the warm-ups of this homework sheet probably. Like there's no reason to just start averaging speeds unless you're trying to do the right thing and then you think you're getting into trouble doing the right thing, okay? Again, if you don't write this down, you don't even realize probably that you're getting into trouble. Like there's a block because we don't know the distance in this problem. So that block will force people to make up stuff that isn't right. I mean, I hope it doesn't, but it often does. Instead, what we should do is stay the course and go to this and look at what we have and say, okay, average speed is distance up plus distance down divided by time up plus time down. That's what it is. And I don't know the distance, but that doesn't mean I should throw away this method. It means, oh, that's probably the issue of the problem. I don't know the distance. I don't know the distance. So now what do I do? My first answer is do not abandon ship because of an unknown, confront the unknown. It's probably the issue of the problem. That distance is unknown, is an issue in the problem. We should directly deal with it. It's not an accident that we weren't given the distance. By this, I mean more specifically, and this is why it's really, really important to write down every step of your thinking. Always write down the things that you think are obvious. The things that you think are obvious, people always think are not worth writing down. They are exactly the things that's worth writing down. A, because I can give you credit for them, but B, because then they generate the next statement. They tell you exactly why you're confused or not. If you write down everything you actually know, it really does make a difference. Anyway, so we're going to do that right now. I'm going to confront the unknown. I'm going to realize, oh, my problem is I don't know the distance of this hill, but that's not my problem. It's not like, oh, I'm misunderstanding this, or, oh, it's an unfair problem. It's, oh, that is the problem of the problem. Confront the unknown means assume the problem is solvable. Now, this is a big step. Okay, now in real life, in real scientific research, actually, you can't always have that luxury. And that's what actually makes the game actually interesting. Doing real research, you don't actually know that the problem you're working on does necessarily have an answer. That does make things even more tricky. But you got to start, but it makes the original idea of solving problems revealed. Like in the first place, the way we're ever able to solve any of these problems, even if they're contrived homework exercises or legitimate worldly problems, is we have to believe there is actually a solution. If you believe there actually is a solution, in other words, if you believe the question itself does not have a mistake in it, and of course some questions do, but this one does not. If you assume the question does not have a mistake, what that actually means here, and this is deep, it means that that unknown distance, that distance that you're not given, actually, yes, you don't know the distance, but you apparently know that the distance doesn't matter. Like if this question is solvable, if there is an average speed to this scenario, and yet an average speed that exists without us telling you how high the hill is, if it's a fair problem, that must mean that the average speed does not depend on the size of the hill. And that is powerful information. I'm saying recognize right from the bat. And you really want, look, let me say again, this is our first, like, I think hard problem in the course. I mean, and I'm not saying, a lot of people might have gotten it right, and they might have gotten it right from the get-go, or they might have gotten it right once I pointed out that it's a little tricky. But this is, I think, our first tricky problem of the semester. It's not, I don't think it's an unfair trick. I don't think it's a trick question, but it is tricky. And the first thing to do is you have to consciously notice what's tricky about this problem is we really only have one equation to work with, one concept, average speed is distance over time. And the one basic piece of information that we'd think we would need, distance, is not given. That is what's tricky about this problem. But that means we have to literally confront that fact, not just sort of like unconsciously think, oh, we're misunderstanding something, or let's like do some weird thing over here. I'm saying we don't know the distance of the hill. But if there's truly an answer to this problem, that means we must recognize, we must recognize the round trip average speed. In other words, the answer that we're looking for. That must mean that the final answer to this question is the final answer to this question, regardless of hill size. That the answer to this question must work for any hill size you pick. If that's true, that's going to be astounding in itself, maybe as an astounding discovery. But it's astounding. It's not an end discovery. It's a pre-discovery. It can help us make all the difference in solving this problem. If I believe that there's an answer to this question that would be true whether the hill was 5 miles high or 1 mile high or a half mile high, then that means I can do this problem without knowing how high it is. And I do believe that's true because this is a problem in the first place. Well, I believe, in other words, it doesn't matter how big this hill is, we can still get an answer. Now, you don't even have to believe that, but I can guarantee you that even trying it out as a belief, even trying out that belief for a minute will allow you to prove whether the belief is true or not and what the answer is. In other words, I'm going to dive in. I'm going to now this attitude, I'm dwelling on this problem because I think this is where physics starts to get interesting with simple stuff. I'm dwelling on this because I want to try to advance the philosophy of problem solving that really comes from the audacity of believing that the earth can move. I want to say the laws of physics are the same in all coordinate systems, at all velocities. It doesn't matter if my coordinate system is here, centered here with an origin here, or my coordinate system is over there and I call that the origin. It doesn't matter if my coordinate system is moving past me at 5 miles an hour or 100 miles an hour. The laws are the same in all coordinate systems. We therefore pick a coordinate system that is, like all coordinate systems lead to the same answer in physics, but some lead to it much more conveniently than others. The idea in physics is whenever we have a choice, we use that choice to our advantage. I'm going to literally, and this, I think to some people, this will sound like a very non-scientific thing to do, but I think it's very scientific. I'm going to assume, or you could call it conjecture or posit or hypothesize. I'm going to declare a size of the hill that is just a number that I feel like I could work with more easily than other hills. And I'm going to see what happens more easily than other numbers. And I'm going to see what happens with this number. Like, I believe that any number I work will get me the right answer. But I also believe that you have no reason to believe me on that exactly. So what I'm going to do is I'm just going to pick a number and see what happens. And maybe I'll then pick another number and see what happens again and see if my answers vary or not. Like, there's no reason as an actual scientist, if I'm first confronting this, that I wouldn't do stuff like that. Like, that's what a lab is for, trying things that are reasonable and seeing what happens. What I want to say is, even if you're in an exam, there's every reason to do what I'm saying, like poke around, try things, think things through, especially if it's untimed and take home, which it will be here. Like, the thing to learn what to do in physics is, well, the thing we're trying to learn is what to do when you don't know what to do. And what you want to do is treat everything like a lab, even in your own brain. So I'm going to let the size of the hill. So let the size of this hill. Oops, sorry. And by the way, when I'm done with this, I'm going to show you, like, if you don't like this, it's, I promise, not the only way, but I want to show you because it works. Let the size of this hill be, now I'm going to say 120 miles. That's a very, very long hill. That's maybe hard to picture, 120 miles. Why wouldn't I just pick like 1 mile? Well, because dividing 1 by 40 and dividing 1 by 60 is like a big pain in my butt. But if I make the hill 120, I feel like that number is easier to work with things like 60 and 40. I picked it because it's the lowest common multiple of 60 and 40. You could pick whatever you want, but to me, I mean, I believe you could pick whatever you want. And that's what we're about to test. But oops. Okay, so this is why I'm choosing it. You could, again, I believe you could choose any number that works for you. I believe this number will work for me just to make my math easier. We will see. Choose it. But so I'm going to choose. So I'm going to say, let the hill be 120 miles long. That would mean up the hill. So therefore, So we're assuming that now. Assuming the hill equals 120, then, okay, then distance, oops, sorry. If that assumption is true, like that, so that is an assumption. That is a guess or a makeup thing. But now I'm not going to make up any other guesses. I'm just going to do everything based on that guess, right? If that assumption or that guess, or whatever you want to call it, these are miles, then the distance up would equal 120, right? And the distance down would also have to equal 120. Like once I make up one number, it follows that both distances are the same. But then the time, well, what's the time up? The time up has to be the distance up divided by the average speed up, right? I'm just rearranging the equation. If speed is distance over time, then distance equals speed times time, and time equals distance over speed, right? Like that's cross multiplying twice, but in fact, let's just make this let's just make this absolutely clear that if, I'll do it on the next page. Hold on, I'll do it on the next page. Time down equals distance down over average speed down, right? Just to be consistent. And I'm going to write this on the next page. I'm saying if you do this in equations, like if V equals X, this is just to remind you. If that is true, then this is true. Right, I can multiply both sides by t. But it's also true that I can do this. I just make sure we're all on the same page. Like if average speed is distance over time, or if average velocity is displacement over time, then displacement is average velocity times time, and time is displacement over average velocity. Yes, like, so if that's true, so here, back to here again, here, so time up must be 120 over 40, right? Time down must be 100. If we're assuming 120, which I just made up, right? But not because I'm the physics professor, but because I'm doing physics. If the hill is 120, then the time up is 120 over 40. The time down is 120 over 60, right? So time up equals 3 hours. Time down equals 2 hours, right? Like, and again, let me say, if we're assuming that whatever is up is down distance-wise, then I'm saying here, if the hill is 120 miles, then on the way up, when he was driving 40 miles an hour, when he was driving slowly on the way up, he had to go 120 miles. He was going at a rate of 40 miles an hour. So it took him this long, ponderous 3 miles to get up there. Then on the way down, he's doing the same distance, but he's going faster. He's going faster, so it's going to take less time to come down, right? He's going 60 miles an hour now, so it takes 2 hours to come down. Put another way, if he came down at 80, if he were going twice as fast on the way down, it would take half as much time, right? Like, do dwell on this for a second. I'm saying if I make up the hill distance to be 120 miles, if I make it up to be 120 miles, I think it makes sense that on the way up, it took him 3 hours, and on the way down, it took 2 hours. Like, it takes more time to go up because he's going slower. But it's not just vague. It's not just more time because slower. It is, he's going 150% as slow. He's going 3/2 as fast on the way back down. He's going 1.5 times as fast on the way back down, 3/2 as fast on the way back down. So the amount of time elapsed is 2/3 as much, right? If he were going twice as fast on the way back down, I think it would take him, he would get down twice as fast, like in half as much time. But here it's 2/3 to 3/2. I'm going to say it one last time and then I'm going to move on for a second because I want you to see something. I think if I made up that the hill is 120 miles, which I made up that number because I think it's easy to work with, but if I make up that number, then it seems like it takes him 3 hours to go up and then 2 hours to come down. So then I put it all together now. So for round trip, remember, what I'm looking for is average speed for the whole round trip. So that means total distance. I'm just looking at the time. Yeah, total distance divided by total time. Well, we said that is equal to distance up plus distance down. So distance up plus distance down. I'm being very careful. I hope you see for a reason, because I could be a little less careful and I could get a different answer, which would be wrong. Time. Like, in other words, I'm doing distance up plus distance down all over time up plus time down, because to me that means that's the same thing as saying total distance over total time. Notice, in other words, I'm not adding two different fractions. I'm making one big fraction out of two different sums, for whatever that's worth, right? So the numbers of this, according to everything we just said, is equal. So the average speed for the whole round trip, according to the numbers we're getting here, is 120 miles up plus 120 miles down. Again, right? Round trip, 120 miles up, 120 down, plus the 3 hours, divided by the 3 hours up plus, well, I'm sorry, I'll make this even more. Right? I'm just copying the numbers from what we just did. 120 plus 120 over 120 divided by 4, right? Distance divided by speed, giving me time. 120 divided by 4, 3, plus 120 divided by 60. I'm sorry, 120 divided by 40, which is 3, plus 120 divided by 60, which is 2. In other words, okay. The first thing I want to say is, if I do it this way, I get an answer 48. I still have more to say, for good or for bad, but if I do it the way I just said, I get the answer 48. Now, the way I just said is a little weird to many people. The way I just said was literally make up a hill distance and see what happens, and you'll get 48. Now, of course, that is not totally convincing to everybody, because first of all, why would you have the guts to just make up a distance if you weren't used to this? And second of all, even if you made up a distance, how have I proven to you, like, how do you know I just didn't pick exactly the right distance? What if you picked a different distance? How do you know you get 48? Well, the first thing I want to say is, yes, I picked 120 because I thought it'd be convenient. But look up here in this step. We have 120 here, 120 here, 120 here, 120 here. We could have factored out that 120 from the top, right? And factored out from the bottom and divide and multiply this entire fraction by 120 over 120. And you'll see it, and it would cancel out, right? And I'm going to show you that a different way in a second. But notice the 120. Like the one thing I made up was that the hill was 120. That was the crazy physics professor, like who said we could do that kind of thing that I did. I made up a hill distance of 120. But what the first thing I'm trying to say right now is that hill, the one thing that I made up totally canceled out. It actually did not matter at all. Right. I mean, if I had made up 240, there'd be a 240 in the top, but then there'd also be a 240 in the bottom. It canceled out. Put more specifically, if you really want to be convinced, let the hill distance just be called X, right? If we want to cut to the chase, like again, say you didn't know to do this, because that's the real thing. Like, why would you know to do it this weird way? Say you didn't have the guts to make up a hill distance. I still say that if you, once you get used to these kind of things, you would still know the hill distance can't matter because it wasn't given. But even if you didn't know that, what you know is that you need the hill distance, but you don't know what it is. So you call it something, call it X, and try to solve the problem around X and see what, like the real thing one of the things I'm trying to say is that people often will say they understand how to do physics problems, but they don't really understand how to start them. If they just knew what equation to use, then they would know what to do from there. Well, the first thing I'd say is yes, but that's the issue of the physics problem is how do you start it? Like that is what we're trying to learn. But the way to start, but really the other thing is the way to know how to start a physics problem is to recognize that you don't actually have to know how it's going to end up in order to start. People are very used to people don't like writing things down that are wrong in science classes. So they don't like starting things unless they can see already where it's all going to land. That's not how physics works. We don't see where it's going to land until we land, but we start nonetheless. So we say, I don't know what the distance is, but I'll call it X and see what I would do with it, and I'll do what I'll do with it and see if I can find anything out along the way. If the distance is X, then according to what we just did on the prior pages, but I can write more general now, then average speed for the whole round trip will equal, if you think about it, X plus X, in other words, 2X, like distance up plus distance down, over X plus 40 plus X plus 60. No matter how you slice it, honestly, the most correct way to solve this problem, if you want to put it this way, the actual way to solve this problem and get an answer, even if you don't know, or especially if you don't know where things are going to land when you start, is to say average speed is total distance over total time. The total distance is 2X. The total time is X over 40 plus X over 60. If you think about it, right? I mean, I'll write it again on the next page. So when you put it this way, what you say, oh, sorry. Yes, I will totally be posted. Yes, and so again, yes, all these, I will definitely post this. Right, hopefully these postings become more and more important as I'm getting more and more things. But yes, this will be posted tonight, absolutely, at one of those links above, or if someone has an improvement on the link, please feel free to. But yeah, when I write it like this now, And again, I'm saying this is the actual way to write it. If you really don't, if you're really just trying to solve this problem, honestly, for the first time, and you don't know what it's going to look like in the end, this is true, right? Total distance over total time. And this makes it stark two things to me. One, it makes it stark that the x's cancel out. And that's the key thing, that's saying right there, aha, whatever the distance is really doesn't matter, because the distance up affects the distance up affects the whole problem the same way the distance down does. Put another way, what this problem is saying is really how is this? The facts of the problem are that you go up the same distance at 40 as you do come down at 60. No matter what you put in for x, you'll get 2 over 1 over 40 plus, right? I mean, that's what the math of this problem reduces to: an ugly looking fraction, but a solvable fraction, 2 over 1 plus 40 plus 1 plus 60. Well, how do you do that? You have to add fractions that are in the denominator, and then once we add them together, then we'll flip the whole thing, because we don't like having fractions in the denominator. To add fractions, you do have to get the lowest common multiple. So when I made up the hill, I was just sort of anticipating this, but so I'm just going to write this again on the next page. I mean, but again, notice these numbers I'm putting in here, nothing is made up now. This is what the problem is if I make up nothing about it, just by virtue of the way the problem is solved. So I'll say this. Right, this ends up looking just like, right, you see what I'm doing? I'm multiplying this by 3 over 3, because that's the same thing as 1. I'm multiplying this by 2 over 2, just so I can make the denominators the same, right? So then I get 2 over 520. So that's the same thing as 2 times 120 over 5. And so I get this 240 over 5, the 48. I'm saying this is still the answer, 48. A minute ago, I got 48 by assuming, by making up a distance for the hill. But now I'm trying to show I didn't have to do that. That was a confident, cocky thing I did because I thought it'd be fast. But even if I don't know that, I don't have to make up a distance of the hill. I can just call it x. I can call it whatever. It cancels out. That's why the problem is possible. And no matter what I do, I'll get 48 as the answer. I'm still not done. Hold on. I mean, and I can go back to this page anytime. The answer now let's back up and look at this for a second. Like, I'm showing right ways to do this, but the real tacit thing I'm saying is what would be wrong is to say average speed is the average of 40 and 60, 50. I'm saying that's wrong. But I think it's very fair still at this point to be asking, but why is that wrong? Like, how would I know that that's, I mean, technically it's wrong because I never said that the definition of average speed is the average of the speeds. We never said that. Like, let me really make it clear. Like, the first thing I'm trying to say is if someone's asking for the average speed, start with the known definition of average speed. Don't make up something just because it looks like we're missing information. Don't make up the idea that you can average speeds in order to get the average of the speed. But it is still also reasonable to say, but wait, but then why do they call it that in physics? Like, that's just dumb. That's just annoying. Then why are you going to call it average speed if, like, it's not even the average of the speeds? Well, it is. Average speed is, in the strictest sense, it is Okay. What does average actually mean? What average actually means is the one value that's best to choose if you want to pretend values aren't changing. Okay, I mean, let's just think about that for 1 second. Like, because there's different ways to get averages, there's different ways to compute averages, but there's one thing that average means. It's, again, it's like a double equal sign, triple equal sign thing. When you take your average in a class after exams, right, is the one number that we assign to you, that we believe is fair to assign to you, even though you have earned lots of different numbers in a class, right? Like if you take 2 exams in a class and you get a 90 on one exam and 100 on the other, the reason you are okay with us saying you're a 95 student, like if we say to you, you're a 95 student, you're going to get an A in the class, you know, what we've just done is totally janked you of 5 points that, like, one of the times you took an exam, you actually got 100. But we're saying you're like a 95 student, even though you got 100 one time, because the other time you got a 90, right? Now, you never actually did get a 95. If we say your average is a 95, we're saying if you, the 95 is the one number we could pick that would allow us to pretend that if you got the same test score all the time, that's the one it would have been. Like, you actually were getting different scores on different tests, but you'll accept a 95 because even though it's 5 points lower than the best test you ever took, it's also 5 points higher than the worst test you ever took. In other words, the average value is a lie. It's a fiction. The average value is the value that did not happen all the time, but is equally far away from all of the values that did happen all the time. It's the lie that is equally far from all actual truths. That's what an average is, right? So in the case of this car, okay, the average value is the best representation of an entire interval during which things are changing, right? So I'm saying if you got a 40 on a test and a 60 on a test, okay, if God forbid, and I can't imagine this happening, this shouldn't happen. If you're in this class, imagine you took 2 exams and you got a 40 on one and a 60 on the other, then your average would be a 50. Absolutely. If you took 2 exams, you got a 40 on one, 60 on the other, your average exam score would be a 50. And we all agree on that. This car may seem at first sight to have done 40 miles per hour and then 60. And so it may seem like we average the 40 and 60 and get 50. But what this car really did was much more like this. Oh, sorry. And so this says, sorry, this page right here says if, meaning if and only if you took 2 exams and scored 140 and 160, then 2 ends, then and only then your average would be 50. If you took 2 exams, got a 40 on one, a 60 on the other, then your average would be 50. But if Wait. Oh, wait, this is a good question. Hold on. This is what I'm talking about now is actually not uncertainty. Hold on. Good question, but this is not about, this is just about averages in general. What I'm saying here is if you took a 40 and a 60, we would average those two things and say you got a 50. But if you got a bunch of scores, if you took a bunch of tests and you got a bunch of 40s and you got a bunch of 60s, if those two bunches were the same, then okay. If you got like 3 40s and 3 60s, okay, then that's the equivalent of getting a 40 and a 60. You're spending as much test moments getting 40s as you are getting 60s. But if it's more like this, say you got 3 40s and you got 2 60s, right? This is the important distinction. Then your average would not be a 50, right? Then your average would be, then it would be like 40 plus 40 plus 40 plus 60 plus 60, all divided by the total number of tests, 5. Or put another way, if you got tests like this, what you might say is it's 40 times 3 plus 60 times 2, right? All divided by 5. It would be still an average, but it'd be a weighted average. Your score would be a lot closer. Well, not a lot. Your score would be closer to 40 than it would, your average score would be closer to 40 than it would to 60 if you were getting 40s more frequently than 60. Your average would be, in fact, 48 if you exactly got 3 40s and 2 60s. And that exact example is the exact example at hand. In the case of test scores are the independent variable. It's like, or each test, each exam is the independent variable. In the case of motion in the car going up the hill, coming down the hill, the independent variable for measuring average speed is time. This car spent more time traveling at 40 miles an hour than it did traveling at 60 miles an hour. How do I know? Because it traveled the same distance. Like it went a certain distance at 40 miles an hour, and then it came back that same distance, but at 60 miles an hour. So it came back that same distance going a lot faster. So it spent less time traveling at a speed of 60 miles an hour than it did traveling at 40 miles an hour. If it had spent half as much time on one speed than the other, it would be like if it spent twice as much time going 40 as it did going, say, 80, it would be like 40 plus 80, average all together, divide by 3, and get an answer. Here, we're going 3/2 as fast down as up. Therefore, we will spend 2/3 as much time going down as up. Like it is here. In other words, if you just want to do a straight up average, you really don't want to just average 40 plus 60. If you really want to average, what you really want to do is it's 40 miles per hour times 3 plus 60 miles per hour times 2 all over 5. That is really what's happening here because, again, we're spending 3 times as much time at the number 40 as we are at the number 60. So in the end of the day, what I'm saying is, at the end of the day, I'm saying for equations, V average velocity equals total displacement over total time. Total displacement over total time will give you the average velocity for a situation. You might have to work hard at getting the distance or getting the time or working around it or something. But total displacement over total time gives you average velocity. And the average velocity you get is the average of velocities, but it's a weighted average. It is carefully taking into account how much time you spend at every speed. So you don't want to just assume, So we're not saying that the definition of average velocity is simply the average of two velocities. Not true. So the answer to this question is 48. Let me pause for a second. So that's the Hill figure question. I'm just going to step away for a second to blow my nose, actually. But tell me, think about that for a second. Tell me if there are any questions. In 1 second. Okay. So, I'm sorry. Last thing about that is, so 48 is the answer. I think no matter how you do it, you can't rightfully get the answer 50. You can think the answer is 50, but it really isn't. But also notice the answer is closer to 40 than it is to 60. Like the answer is something slower than 50 because again, we spend more time doing the slow speeds than we do the fast speed. So it makes sense that it'd be closer to 40. The question of how much closer to 40 is the ratio of the speeds. Right, so I think the answer is 48. Any questions on that? And we have 15 more minutes. Okay. Okay, I want to move on. Well, I'm going to now write down, I'm not going to talk as much, just to wrap this up. The very next problem on that sheet, the Little Red Riding Hood problem, is the exact same kind of issue. Once you get this, it works the same way with this next one. And the catch again is don't just randomly average speeds in order to get the average. But what I'm going to do this time is I'm going to write down how to do it. I'm not going to talk, I'm just going to write down. So if you, so hopefully it'll allow you to quietly think about this now, whether you did it right or wrong. I'm just going to, and then you can ask questions, but I'm going to just write down how I did this next one. And if you want to take this moment to rethink it for yourself for the first time, feel free. Okay. And I forget what the problem is called, but it's something like Grandma. Oh, Grandma Grimm, maybe? Yeah. Okay, just to remind us what the givens are, we have a distance of 80 kilometers, like from here to Grandma's house, I think, right? 80 kilometers, and that's known. What's also known is that Little Red Riding Hood goes out to Grandma's house and does so at an average speed of 40 kilometers per day. I mean, all these numbers are ridiculous, but they're fair numbers. So she goes out at an average speed of 40 kilometers per day. You can even picture that as a constant speed if you want. Like, I mean, we don't know what she's doing at any given moment, but we know on average, she's averaging 40 kilometers per day, okay? And the ultimate question is how fast should she return such that the entire round trip speed clocks in at 80 kilometers per day. That's the question. And I'm not writing this well, but such that, I'll write this again on the next page. Okay, I'm going to write this again on the next page. But the givens are that it's 80 kilometers of distance out there, and that she travels at a speed of 40 kilometers per day. Those are two givens. And the other given is that she wants her round trip average speed for the whole thing to be 80 kilometers per day. So the question is, how fast must she come back in order for that to happen? Right. So I'm just going to write down again. So again, givens. I'm not going to write the diagram again, but givens. Distance out. Oh wait, I said I wasn't going to talk about this, didn't I? But all right. Well, these 80 kilometers. Average. Yeah, I'm going to stop talking. I'm just going to write this. Okay, right. These are the facts. This is the question, and we're gonna end. I keep saying I'm not talking about. I'm just doing it, but I don't know. But this is the last thing we're gonna do today. We end at 1:30, I believe. Right. Okay. So so we want to know how fast she should come back in, so that her average speed for the whole thing is 80 kilometers per day. Okay. Well, this is just like last time. The average speed of the round trip must be total distance total, right, over total time. In other words, equals. Okay. Well, we know the distance out is 80. We know the distance in is going to be 80 again. The total distance for the whole thing has to be 160. We know the time out. We don't know the time out, but we do know the time out. We know the time out must be 80 kilometers distance out divided by that speed of 40 kilometers per day, right? And we don't know, what we don't know is the time in. In fact, really tacitly, that's what we're trying to figure out. How fast does she have to come back in? Well, in other words, how much time will she take to come back in so that this all works out? So we don't know this. Well, okay, so we'll go on the next page now. We're about to end on this. Right, the one thing we don't know is the speed on the way back. That's what we're trying to figure out so that all these other things work. But okay, so what we have is if you just look at the numbers, what I'm saying is the only number that you could put under 80 to make the whole fraction equal what it needs to equal is infinity. Like, if you look at these numbers, there's nothing we can put in that question mark to make this work out. What we're really saying, if we look at these numbers, is if she wants her round trip speed, if she wants her average speed for the whole round trip to be 80 kilometers per day, since the whole trip is 160 kilometer trip, right? That really means she wants to do the whole round trip in 2 days. That's what it really, if she wants the whole round trip to have an average speed of 80, then the whole trip is 160 kilometers long. She needs to do the whole trip in 2 hours in order to satisfy the requirement of the question. But she's already taken 2 hours to go out. That's really what these numbers are saying. That that she would have to go some speed on the way back such that she takes only 2 hours to do the whole thing, but she's already used up the 2 hours to go out. So the answer is infinity. That doesn't mean that there's no answer to the question. It means there's no physically possible answer to the question, but the answer she'd have to get to back from her house in no time at all. Again, what's the lesson? The lesson is average speed is defined to be total distance over total time. Average speed is not defined to be average of speeds. I sometimes let you late and all that stuff. That's, you have no new homework or anything. And in fact, I would say watch the other video, but you don't have to, you're good. I mean, the other video is just like this one. So watch this if you missed anything, but so you don't have anything new. I have to catch up with you guys still. Let me say that again. You don't have anything new for Wednesday. But if you are somewhere in the homework, please keep going. Just keep going in order. So the video, did we answer? Yeah, if you look in the chat, well, yeah, I think, and someone could correct me. I mean, so the YouTube channel is called, and the link at least to could someone correct me? If you put a link, this link that I put in is to a playlist, like it's not, but I think once you're in that playlist, you can just get to the channel, right? But I'll change the link so it goes directly to the channel itself. Oh no, you can't, that's the problem. But anyway, so these work. But yeah, if you have no questions on, since there's no new work or anything, if there's no questions on this, I'm good. If you guys are good, if anybody wants to ask a question right now, please do. But I will post this and I'll send around the notes right now. But again, if there's no questions on this, I'm good. If you're good, oh yeah, oh sorry. It's actually, technically, the name of the YouTube channel really is weirdly Prof. Yeah, like there is a space after the period, I'm pretty sure, and there's no. Here, wait, let me do this right now. I could try this right now. Because I think it's just hard to do. For some reason, a direct link just to a channel seems harder than to a playlist. That's why I keep making the link. But I believe it is, and I'm checking right now. And again, anybody can go, or if someone can help, that would be great. But it is, I believe that it really is like this, that you type in to YouTube. I'll do it right now. But again, anybody can leave. I'm good if you guys are good, but here, all right. Oh, thank you guys. Have a nice day. All right, yes, you can leave. Here's the, thank you. Oh, where it is going. Okay, this, I think, this is the channel. I think that's, yes, I think what I, so, yes, feel free to go. Whoever you are, everybody. Uh, all right, so I'm going to end. Thank you all very much.